Welcome to the first chapter of General Chemistry 1. We are going to be breaking this chapter into several different parts so that way you're not overwhelmed with the videos. After each chapter, we're going to go over questions and make sure you know how to do problems. This chapter is going to focus on the basics of chemistry for some of you guys. If you took introduction to chemistry, this might be repetitive. Just hang in there. As always, write down the slide so you can ask me questions later on. I want to start by emphasizing how easy things will be if you memorize the first 50 elements of the periodic table. Um, we can Google the periodic table. You can request a periodic table. There is a periodic table on your textbook. What I mean by your 50 elements, I mean I want the name, the atomic number, and the symbol. You may not know what that means yet, but for example, if you look at number 1, you're going to see a 1, you're going to see an H, and you're going to see hydrogen. The 1 represents the atomic number. The H represents the symbol, and of course the name. So you are responsible to knowing all three from number 1 to number 50. Once we get later on, we're going to have to memorize how to name. So if you know these elements, it will make your life much easier. Moving on why some of you guys have it's part of your prereqs to take a chemistry course. And the reason for that is because chemistry is related to many different topics, from working as a vet, from being a pharmacist, from working with your body, because you need to know how the cycles in your body works, how do we digest, or how much medication to take, from working at a restaurant as a chef. To be honest, chemists are the best chef because they know the ratios, they know the amounts. So no matter what field you decide to pursue, you will need chemistry as your main, as your foundation. And if your foundation is strong, that is going to help you succeed later on. So it's very important. Physics, even if you take physics, you're gonna see that later on we're gonna be doing quantum mechanics, and physics is involved. Even if you take computer science, right now that's where the money is. So whatever you decide to do, chemistry is your foundation. So might as well learn it, be good at it. That way you can be successful in whatever career you decide to choose. Now we're gonna start looking at how chemists, you guys are chemists now, you're taking a chemistry class. How do they think? Why is it that a lot of people say that chemistry is a tough subject? The reason for that is because we never stop asking ourselves questions. We don't want to just know how things happen. We want to know why things happen. The difference between chemists and biologists is that we care about whether something is alive or something is dead. We care about everything. We question ourselves is why is there a rainbow? Why is those colors next to each other? Why is it the violet is the strong color? Why is it that when I open a soda versus being warm room temp soda or cold soda, the fizzing that you hear is different? So those type of questions is that you're asking yourself. You're constantly asking yourself. And now obviously can be overwhelmed if you keep asking yourself these questions, right? So there is a method of trying to answer these questions. I say the word trying because we never get to a final answer. You know, we probably have some data that represent it, but once you start doing that, then you will come out with the questions that you're going to try to solve. So it's just a cycle. But what we're going to be going over is the scientific method. And the scientific method, you probably have heard it before in your other courses. We follow our order is a little bit different than everybody else's. So focus on the one I'm going to go over. So for our scientific method, pretty much it's just this set of rules that kind of like allow us to try to answer that question or to put our ideas together. We start by asking ourselves, being doing observations. Observations means you're seeing a trend or you're seeing some data that keeps recurring. So you're just observing. After that, you have hypotheses, theories, law, experiments. So let's start just by observations. Observations is what you're going to be doing in your lab. You're going to be taking notes. You're going to see how something bubbles, or something changes colors within what time. So all of that observations sometimes are also known as data. You're collecting. You're trying to just figure it out things. You're seeing a pattern. This is very important. We actually have Alexander Fleming, who through observations was able to discover penicillin. Just because he started noticing something, started recording it, and it's very important for you to record your data. Now, what happens after you have recorded all this data? You're going to come out with you're going to formulate a hypothesis. And that hypothesis is pretty much an explanation. It's an explanation um, of your observations. Now, this explanation doesn't have to be correct. This explanation actually someone else should be able to prove that it may be wrong. This is just an explanation. Why does it necessarily have to be correct? Because it's a hypothesis. In order for us to determine that it's correct, there has to be testing. It has to be go through an experiment, which brings us to the next level. Hypothesis must be tested. And we tested with controlling numbers to be able to manipulate our data, be able to test it, and make sure that our results match what we thought, right? Now, after hypothesis, or within hypothesis, after that, we can go to laws or theories. After we test our hypothesis, we can follow by laws and theories. Now, laws and theories also have to be tested. Um, but think of it as to get to a law or a theory, you have to have done way more testing than just to get to a hypothesis. Moving to a scientific law. A scientific law, especially for chemistry, is typically very short. It's a mathematical expression. It's pretty much, the goal is to tell you this is it. You just follow that. It's a specific statement that is telling you, here's the formula, just follow it. It doesn't tell you why. It's just going to just give you the information, and it's going to tell you, hey, here it is, follow it. Sure, it doesn't explain the bigger picture. On the other hand, we have a theory. A theory is more established. It's a well-established hypothesis. What that means is that it has been through years of testing. A scientific theory is a model for the way nature is behaves, and it tries to explain not why things happen, but also how things happen. So that how and the why. Um, Theories as well as hypotheses and laws are going to be validated through experiments. Theories can never be conclusive. What that means is that a theory can potentially have a flaw, and we see it time after time in chemistry where we have come out with a theory, but years later, we have someone else find that flaw in that theory and we develop something new. So it's a process. So as you can see, this chart kind of summarizes the scientific method and the order that we tend to follow. Notice here, a theory set of conceptual assumptions that explains data accumulated from experiments and is able to predict. A theory is able to predict. You always are also going to have you also are going to have experiments, right? Through my slides, you're gonna see that you have slides that's called Check Your Understanding. This is for you to take a minute, read the question, and try to answer it yourself. So I will give you a minute to read it and try to figure it out whether the statement presented to you is an observation, a law, or a theory. Okay, the first one is an observation. Letter B, it's a law. Letter C is a law. Letter D is an observation. Moving to the next one. The answer is going to be a scientific law. For this, the answer is a law. Law states a consistently observed phenomenon that can be used for a prediction. B is going to be a theory. Remember, a theory is a widely accepted explanation. And third one is a hypothesis, which is a tentative explanation. Okay, so that pretty much covers the first part. Not much, you're not gonna be tested a lot on it, probably 1 or 2 questions. Moving on to our second topic, which is the main topic. What is chemistry? Chemistry is the study of matter and the changes that matters undergo. So it's not, just what matter is. No, we are actually more concerned on how that matter is going to change. So for you to understand how it's going to change, we need to go with the basics and figure it out. What is matter? Matter is going to be anything that takes volume and that has mass. For example, the chair or the bed that you're sitting on right now is composed of matter. Liquids is composed of matter. We have some definitions here. As you can see, composition, the types and amounts of simpler substance that we can make up a sample of matter. Properties, the characteristics that give each substance its unique identity. We are going to classify matter according to their state. What I mean by that, its physical form and its composition, the basic, what makes it up, the matter. So we're going to classify it based on the state and its composition. The physical states of matter are going to be your solid, your liquid, and your gas. We are going to go over some of those properties. In a solid, the matter particles are going to be packed. They are going to be held tightly in a fixed location. They are not, even though atoms or particles, I'm gonna define that later on, are constantly moving, vibrating, in a solid state, they're not gonna vibrate as much. As a result, solid have a fixed volume and rigid shape. And I'm sure you guys are aware of an example of solids. such as aluminum, diamonds, a glass. All of that will be an example of solid. When it comes to solid, we are going to have two types. We have the crystalline and we have what's called amorphous. Crystalline, the atoms or molecules are going to be in this long range repeating order, this organized. So there's going to look organized. Those atoms in there are going to be in this um, pattern that looks organized with certain angle between them. So that's called crystalline. An example of a crystalline would be diamond, salt, anything shiny, anything crystal. On the other hand, we have amorphous. In this case, what happens is that the atoms or molecules in there are all disorganized. They do not have this long range order. And we are talking about graphite, glass, plastic. That's what I will be referring to. Now we're gonna move on to liquid. Liquid matter, the molecules or the atoms are still packed, but there is more space between them. There's not as tightly held like they are in your solid. They have a fixed volume, but they do not have a fixed shape. In a solid, it has a fixed volume and a fixed shape. Liquids are going to have the ability to flow, and they're going to assume the shape in whatever container you put them on. On the other hand, we have your gases. Your gases are going to have lots of space between them. They are going to move freely relative to one another. They are going to be able, you can compress them and you won't be able to destroy the gas. It does not have a fixed volume or a fixed shape because they're just random. Some examples of it is oxygen, which is one of the elements, and that symbol is O. Helium, the symbol is He. And then carbon dioxide, which is a compound now, it's going to be CO. Those are example of gases. So summary, we have a table here, which pretty much just summarizes the last few slides that I went over. Coming up, we have some more check your understanding, and please try to answer them yourself. The answer is false, because chemistry is the science that tries to understand how matter behaves by studying atoms and molecules. So not necessarily just living organisms. Moving on, matter is made of atoms. Atoms are going to be microscopic particles. These very, very small particles. And those particles are like the building blocks of everything. Back in the day, they used to believe that atoms was the smallest particle that can exist. You cannot break down a atom. We're gonna see how that's not true. So if we look at the composition of matter, remember I told you that we're gonna go by the state, which is the form, solid, liquid, or gas, or the composition. So now we're looking at the composition. Matter can be a pure substance or it can be a mixture. Or if it's a pure substance, it can be an element or a compound. If it is a mixture, it can be a heterogeneous or homogeneous. So let's start at the top. Matter, we're gonna see whether it's a pure substance or not. When we're looking at pure substance, we're talking about just being composed of one type of component. So it's only one type. For example, water. it's only water in there. But pizza or your, I don't know, salads, that becomes a mixture because you have different components in there. It's not a uniform. You are aware that you like having a mixture. Now we move on to, if you do have a pure substance, you have to ask yourself whether you have an element or whether you have you have encountered a compound. An element is what you're going to, sorry, that says 36, it should be 50. An element is what you're going to encounter in your periodic table. As you can see, an element is going to be represented by a symbol, either one letter or two letters. If it's only one letter, the letter will always be capital. If it's two letters, the first one will be capital and the second one will be lowercase. Elements are made of only one type of atom. So inside an element, that's why element and atoms are gonna be interchangeably. We use those two terms because if you look at helium, inside helium, there's only helium atoms. If you look at carbon, inside carbon, it's only carbon atoms. So we have roughly 100, I believe we are up to 118 elements. I think we're up to 118 nowadays. Some of them are synthetic, meaning synthesized outside. Some of them are naturally found. As you can see here, we have AU, which is for gold, and we have capital C, which stands for carbon. Compounds are going to be pure substances. They are going to be made of two or more elements. For example, salt. It's two elements come together, but it's only salt. There's nothing else. So that will be considered a pure compound. We have another one that we have is water, which is H2O. So that is also be considered a pure compound. And the ratio and all of that, we're gonna get to it later. So to see if you understood the slides that I explained, see if you can answer the last column. Basically, for example, water, it's telling you what it's made out of. So is it an element or is it a compound? So take a few minutes before I give you guys the answers. And there are your answers. Moving on, now we're going to focus on this side. We are going to see whether it's a heterogeneous or a homogeneous. Mixtures are going to be classified into heterogeneous and homogeneous. What is a heterogeneous substance? A heterogeneous mixture is going to be one where the composition is going to vary. So you're going to have different regions and you're going to see this mixture. So for example, salt in water or sand, you're gonna see that is a mixture, but you're gonna see the little black things of sand, and then you're gonna be the salt. So you're gonna be able to see the different portions. That's considered a heterogeneous mixture. On the other hand, you have the homogeneous mixture where, for example, your latte, you know it's a mixture because it has milk, it has coffee. However, well, sometimes you're not able to see that separation because they mix in. Or your beers or that's a mixture because it has a lot of things. It has alcohol, it has all of this stuff that it has. You know it's a mixture. However, you're not able to see the carbon dioxide. You're not able to see the different elements that are in this beer. So to summarize, you have this table, which pretty much is what we just went through. So you should be able to give an example of each, be able to identify. Here is a practice table for you to try to do on your own. So you want to determine whether it's pure or it's a mixture, whether it is an element, a compound, a homogeneous or a heterogeneous. So you may want to pause the video and try to answer this on your own. And those are your answers. So that completes the first video. So I don't want to overwhelm you, and we're going to continue. We're not done with the first chapter. This is just to introduce it. I'll see you soon. We are going to continue in our discussion for the first chapter, and we're going to start talking about separating mixture. So let's say you have a mixture, heterogeneous or homogeneous, and you want to separate it into its individual components. If you have a liquid, like for example, just liquids, and you want to separate them, you can use this technique called distillation, which is a process where you separate two liquids based on their boiling point. So the more volatile, which means easily gets evaporated, it's going to easily come off. It's the first one that's going to come off. So for example, this in here will be the one with the lower boiling point, and the one that is less volatile will stay behind. The most volatile will come out first, which is this. Get separated by the water condenser. You don't need to know the ins and outs of how it works. We're gonna wait until you get to organic chemistry for that. So we separate it based on boiling point. Moving on to discussing properties. In chemistry, we have physical and chemical properties. Physical properties are going to be those that change without changing its composition. What does that mean? For example, the smell of a gasoline, it changes. That's a physical property. Or you changing, dressing, putting clothes on, combing your hair, that's a physical property because you're not changing the person you are, just changing the looks. Color, it's a physical property. Melting point, this is important, melting point, boiling point, density are all physical properties. Moving on to chemical properties, these are the changes that take place, but they actually change the composition. For example, acidity, corrosiveness, toxicity. You actually created something else. You started with something and it went to a physical change and created something else. For example, you start with all the ingredients to bake a cake. When you finish, it goes through a chemical property, chemical change, due to chemical properties, and now you're going to have something different. You're gonna have an amazing cake. Within these properties, we have an extensive and intensive property. An extensive property is going to be that property that depends on how much matter is being considered. For example, mass, length, volume. Whenever we're talking about numbers, it's gonna make a difference. For example, 10 liters of water is not the same as 10 milliliters of water. So that is an extensive property. Every time numbers are involved, it's going to be an extensive property. What I mean by numbers, that the amount is going to make a difference, right? An intensive property is going to be an intensive property. It's going to not be dependent on how much material you have. So for example, density. So let me explain that. If you go to the ocean and you grab, I don't know, 1 tank of water, and you uh, calculate the density is going to be roughly 1. And if you go get a bottle of water, the density is still going to be 1. So it doesn't matter the amount, the density is still going to be 1. Um, if you go to the park outside versus going to, I don't know, a stadium, the temperature will be the same. So that will be an intensive property. Going a little bit more on physical change, boiling water will be a physical change, because notice that we went from liquid to gas. You still have the water molecules, but what happened now is that you have more space between the molecules itself. But it's still water, it's just when they change the state. If we look at the chemical change, here we have iron, okay? But when it gets exposed to oxygen, the oxygen is going to intercalate there. So now this molecule is not the same as this molecule. It changed. So that will be a chemical change. There was a change. When we represent a chemical change, we're going to use this arrow. That arrow in a chemical reaction means that those ingredients, those reactants went through a chemical change to make something else. So you probably started with A plus B and you made AB. Here on your left side, we're going to write your reactants, your ingredients, and the arrow indicates that they are going to change into the products, into something else. Here we have some changes. Notice that dry ice subliming is considered a physical change because it goes from solid to gas. Sugar dissolving is a physical change because it goes from solid to aqueous. AQ, that means it's just basically dissolving water. We have propane burning. That's a chemical change because notice how you started with 2 ingredients and you ended up with 2 different products. That will be considered a physical change. Sorry, chemical change. Here's some practice for you guys to try on your own. Determine whether it's chemical, physical, extensive, or intensive. The first one is intensive. Second one, chemical. The third one, extensive. D, intensive. E, chemical. F, physical. G, extensive. Here's another practice for you. Physical, physical, chemical, chemical, physical. Here's another problem. So you can pause it and try it on your own, read it. So, they're giving you to determine whether the followings are a physical or a chemical change and explain why. And here's your answers. We are going to switch gears a little bit and we are going to start talking about energy. Energy is a capacity to do work. What is work is defined as the action of a force through a distance. In general, lower energy is always going to be more stable. Compounds, atoms prefers lower energy. Want to remember that energy is neither created nor destroyed. Energy is conserved. However, it can be converted from one object to another. We have 2 types of energy, two main types. We have kinetic energy and we have potential energy. Kinetic energy is associated with motion, with movement. Anything that is moving has kinetic energy. The more movement you have, the more kinetic energy you have. Within kinetic energy, an example would be thermal energy. Thermal energy has to do with temperature. So when you heat something up, you're given it more temperature, you have more movement. The other main type of energy is potential energy. Potential energy is associated with the position of the object or the composition of the object. If it's something is high, in like a high position, it's gonna have high potential energy. As remember, I told you the energy is conserved, so we cannot destroy it. So we can do potential energy plus kinetic energy will give us your total energy. They both have to add up to something. We cannot destroy it. The kinetic energy is not going to go away. It's not gonna get destroyed. You're not gonna be able to create it. It comes from something and it goes into something. And we're gonna discuss more energy when we get later on in your chem class. I was telling you, there is actually a law for energy. And that law says energy is always conserved in a physical or chemical change. It's neither destroyed nor created. Energy can be changed from one object to another, or it can be transferred from one object to another. It doesn't appear from, there's no magic. It doesn't vanish into anything. It's transferable. As you can see here, we have an object that it has potential energy. It has high potential energy, so it means it's unstable because of the position. So what that metal is going to want to do is going to want to fall, which means it's going to get converted to kinetic energy, and then it's going to go back to potential energy where it's more stable. Okay, now we're going to start discussing math, and we're going to start by saying how lazy scientists are. We don't like writing big numbers. So what we do is we use scientific notation. Scientific notation is pretty much a shorthand way of writing big numbers to the power of 10. For example, here we have this 20 trillion, I believe it is, has all those zeros. By using scientific notation, I can condense that number and I don't have to write all those zeros. So it changes the length of the number. So that's scientific notation. So for example, this, you're going to assume that there is a decimal point at the end. You're going to move the decimal point to the left between a number 1 and 10, which means here. Now that number becomes 2.0 times 10 to the 22 power. That means you moved it 22 times to the left. So whenever you're moving your decimal point from the right to the left, you are going to be putting a positive exponent. On the other hand, if you're moving the decimal point from the left to the right, you're going to be putting a negative exponent. That means that you are dealing with a very, very small number. A scientific notation has two parts. It's going to have the decimal part and it's going to have the exponential part. The decimal part is going to be basically you moving the decimal between a number 1 and 10. The exponential part, you're going to do times 10 raised to a n. N is going to be either a negative number or a positive number, a full number. So for example, this is scientific notation. If I was to ask you for standard notation, you're going to do, so it has negative 10, so you're going to do 0.1, 2, 3, 4, 5, 6, 7, 8, 912. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now this is negative 10. If the question was 1.2 times 10 to the positive 10, then that will be this. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. I think I put one extra zero. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, one extra zero. So make sure you guys know the difference when we're doing positive exponent or negative exponent. This will be incorrect. 11.2 will be incorrect because the decimal has to fall between a number 1 and 10. Here's some example. Notice how they're giving you this number. This is standard. This is standard notation. And they want you to put it in scientific notation. So you want to locate, you want to imagine that decimal being at the end, and you're going to be moving it from your right to your left. That means that you're going to have a positive exponent, and it's going to be 1.2340 times 10 to the fourth power. On the other hand, if we were to locate the decimal, it looks like we're gonna have to move the decimal between 1 and 10, so it's gonna fall there. We're moving it from the left to the right, indicating that our exponent is going to be negative. Final answer will be 1.2340 times 10 to the negative 4. So this is a very important to make sure you understand that concept. Here are some more practice problems. This is standard, this is scientific notation. Standard, scientific. Pay attention on why this is negative and why this is positive. Take a minute to try this on your own, and I'll put the solutions in a second. Here's your answers. And microliters, by the way, is gonna be this UL, units, microliter. Okay, now continuing the word I say units because we are going to start discussing units. In chemistry, it is extremely important that you put units next to your numbers. Your numbers mean absolutely nothing without units. And we have two common unit systems that we follow. We have the metric and we have the English system. The metric system is followed in most of the world. The English system is used by the United States. Scientists follow an international system of units, the SI system, which is based on the metric system. So you pretty much have to know 3 of them, right? We call it the SI units. As you can see, these are the units you're gonna have to, well, some of them, right? There's more. You're gonna have to remember that the SI unit for length, it's meter, and it's abbreviated with M. The SI unit for mass, it is not grams, it's actually kilograms. For time, it's second, not minutes. For temperature, it's Kelvin. And for amount of substance, we're gonna be discussing mole. So you make sure that you memorize this. This is important for you to memorize. Within the metric system, the SI system, we actually, this is not a correct table, but the table is on your slide, so you don't have to worry about it. We have prefixes, multipliers. And this pretty much are going to change the value of the unit by the power of 10. So for example, when we use kilo means 1,000, but when we use say milli, it's gonna be actually 10 to the negative 3, which also means 1 over 1,000. Okay, so you're gonna have to start getting familiar with those. And basically, it's that table. Everything that I crossed out is the things that you don't have to memorize. Everything that I did not cross out is the things you do have to memorize. Here are some common English equivalents. So there are connecting the SI with the English. We don't have to memorize this, especially the English ones. The English, we're not memorizing that. If you need it, I will be giving you those numbers on your exam. Okay, now from those units, major units, we have derived units. Units such as volume, concentration, density, and pressure. Those are derived. The reason they're derived is because they're combinations. So for example, for volume, it's length, right? Because your length is meter times meter times meter. That becomes your volume, meter cube. So it's a derived unit. For concentration, it's moles over liters. And that's where your volume is. So it's a derived unit. We have density, which is kilogram, which is pretty much mass over volume. This is a unit of mass and this is a unit of volume. We also have pressure, which we have mass, volume, and time. So this is all combined. So they're combined. So volume, as I mentioned, is a derived unit. Basically, it's formed from other units. Many units of volume is a measure of space. Those are derived units. Notice here we have cubic meter, meter cube, centimeter cube, centimeter, millimeter cube. They're all units of volume. And what I want you to emphasize is that 1 centimeter cube equals 1 milliliter. 1,000 centimeter cubes equals 1 liter or 1,000 milliliters. So you want to be able to make that relationship. When we are starting to do problem solving, we want to make sure that we understand the units because we are going to be able to manipulate those units just like we manipulate the numbers. So they go together. You want to be able to manipulate. For example, notice here we have 3 feet times 4 feet. So what are we doing to the number? We are going to multiply it. 3 times 4 equals 12. But we also have to do that to the unit. Feet times feet equals feet square. Notice here, what are we doing? 350 miles in 7 hours and equals 50 miles in 1 hour. Or the way we can write it is by solving it. And that means this is the same as saying 50 miles per hour. This is the same thing. Okay. Moving on to conversion factors. Conversion factors is going to be a ratio of equivalent quantities used to express a quantity in different units. Basically, it's going to be our bridge. Conversion factors are our bridge that's gonna allow us to go from one unit to another. So notice that in here, 1 mile equals 5,280 feet. This is by definition true. Conversion factors are definition, they are true. Here we have a problem that I want you to try on your own. So notice that they're giving you the height and they're giving you this conversion factor. So they want you to set it up. So you are basically converting from feet to miles. This is your conversion factor. is the true definition. Notice how you cancel. Your desired unit is always on top. Your desired unit is on top. When you are doing a problem, you always want to make sure you know what you're being asked. Make sure you plan to clarify what units can you cancel. Is there a direct relationship? Do you need one or two conversion factors? Make sure your answer makes sense. And make sure that you follow up by doing more practice. We are going to switch topics again and still talking about physical properties, and now we're going to be discussing density. Density, as I mentioned, is a unit of mass over a unit of volume. It doesn't necessarily have to be grams or kilograms, as long as it's a unit of mass on top divided by a unit of volume. For example, a liquid has a volume and a mass. So if you want to calculate the density, we do grams divided by volume. And the units do not cancel, so you just leave both units there. Density is an intensive property. It does not depend on the amount of material present. It just depends on what it is. In other words, volume increases and mass increases. Density usually decreases with temperature. This you will need in your lab, so keep this in mind. Okay, most matter increases in volume when it gets hotter. For example, if an iron rod is heated, it will get longer and fatter, and its density will decrease. Why does this happen? Because the mass of the rod stays the same, but the volume, meaning the number at the bottom, is going to increase. The increase in the volume of the matter with increase in temperature is called expansion. I'm sure you've seen this word before. When cooled down, most of the matter decreases in volume and the density is going to increase. And that will be called contraction. Okay, so here we have examples of densities that you might encounter. All of these are units of density. But it's very important that you know that at 4 degrees Celsius, the density of water is 1.0 grams per milliliters. Here we have a problem of density where they are giving us the density of the substance, but they're asking for the volume and they're giving you the grams. Always start with the grams and you have density. This means this, 1.32 grams over centimeter cube, or 1 centimeter cube over 1.32 grams. Now, which one do you want to use? Number 1 or number 2? You want to use number 2 because you want to be able to cancel grams. Okay? Now you're left with centimeter cubes, but you don't want centimeter cube, you want milliliters. So what you're going to do is you're going to remember that 1 milliliter equals 1 centimeter cube. So you're going to use either 1 milliliter over 1 centimeter cube or 1 centimeter cube divided by 1 milliliter. Because you want to cancel opposite top and bottom, you're going to do option number 1. Now the only unit does not cancel is your desired unit, which is going to be your milliliters. And your answer should be in 3 significant figures, and we're going to discuss significant figures later. Here's a problem for you to try on your own. The solution would be 8.1 grams. Another problem that you should pause and do on yourself. The answer will be 4.09 9 centimeter cube. Another question. Pause it and try it by yourself. Answer. Another question. Here's a problem that has been solved for you. Read it in your slides and try it before you look into the answer. Plan it as you see the plan here. Here's your answer. Okay, so I think I gave you enough for right now. We are going to continue and don't pay attention to this. And we are going to move on and start talking about more math problems, temperature, significant figures, and so on. Hello, we are going to continue with our chapter 1. We are going to start discussing temperature. And as you know, the SI unit for temperature is going to be Kelvin. We say that the coldest temperature is 0 K as the absolute zero. That's the coldest temperature possible. 0 Kelvin equals negative 273 Celsius or equals negative 459 Fahrenheit. So we're going to be able to manipulate from one to another. Notice here they're showing you the equivalence. If you have 0 degrees Celsius, 273 Kelvin, and 32 Fahrenheit. What that means that if you want to have Celsius and you need Kelvin, you just add 273. If you have Kelvin and you want Celsius, you subtract 273. Here is if I give you Celsius, if I give you Fahrenheit and I want Celsius, you're going to be able to use this equation and manipulate it. You don't have to memorize it. I will be providing you this, this equation. Moving on to significant figures. So in calculations, you're going to have units and you're going to manipulate these units. You're either going to add it, multiply, and divide it. We have to be careful when you do this math manipulations. In a multiplication and division, the units are multiplied or they are divided. However, in an addition or subtraction, the units have to match. So you cannot go ahead and add them unless they are the same units. For example, this is not correct because one unit is gram and the other one is kilograms. They are not the same unit. So you can either convert grams to kilograms or kilograms to grams. In this case, they converted the kilograms to grams. Since now they are the same units, you can add those two numbers. When you are multiplying or you are dividing, you're multiplying, you're going to multiply the units too. So centimeter times centimeter equals centimeter cube. When you are divided, you divide the units. So for example, this is divided grams over mole. So you're going to represent both units in your answers. Just a general overview when you are solving problems. We kind of already went over this, but I want to remind you to make sure you check the information that is given, make sure that you are able to match it, make sure that you are able to use the correct conversion factors. I posted a video here in case you need a little bit of extra help. We have an example problem here where two conversion factors are needed. Remember, conversion factor is a definition. You start with the given information and the unit that does not cancel is your desired unit, So here we want to go from centimeter to feet. There is no direct relationship, so you have to jump from centimeter to inches. So you're going from centimeters to inches and from inches to feet. So you're using two conversion factors. Centimeters and centimeters, top and bottom cancel. Now you have inches. You want to cancel inches, so you put it at the bottom. 1 feet equals 12 inches, and your final answer will be in feet. Sometimes you have a double conversion. For example, here you have miles and gallons, and you need to convert it to kilograms and liters. So you can, it doesn't matter which one you start with one at a time. Here we're gonna focus on canceling miles. So this is a conversion factor, a definition. Notice here you cancel your miles and you have kilometers, which is what you want at the top. Then you're gonna focus on canceling your miles, right? That's what we did. No, sorry, your gallons. So we're gonna focus on canceling your gallons. So then you want it, since it's at the bottom, you want it at the top. You cancel your gallons, and at the bottom you have liter, which is what you wanted. And your final answer will be kilometers over liter, which is what you desire. Be careful when you are squaring a number or cubing a number. Whatever you do to a number, you must do to the unit too. So for example, here, if it's 2.54 square, the unit is also going to be square. If it is cube, the unit will always be cube too. So notice here, this comes from the fact that is 2.54 centimeter cube equals this. So be very careful when it comes to that, please. This is another example when we're converting kilometers to miles. So you remember, want to make sure you find a conversion factor, and it will probably be given to you. Some of them you guys don't have to memorize it, except for the metric system. Notice here, you are giving kilometers. So that means kilometers have to be at the bottom in order to cancel it. And then you cancel your kilometers and your desired unit will be at the top. It's another practice for you guys to do. I'm sorry. Here's the answer. Those are your final answers. It's another question where we are converting from meters to yards. The answer for this would be 96.71. Moving into a slightly different topic, let's talk about accuracy and precision, which you're going to be doing in lab. Accuracy is how close a measurement is to the accepted value. Precision is how close a series of measurements are to one another or far out a measurement taken. For example, you have, let's say you have 3 students in the lab, and you ask the student to go weigh 10 grams, 10.00 grams of, I don't know, acetylsalicylic acid. So you have the student A, they did 4 trials. This student was all over the place, and the true mass is 10, but it was up and above. So we say that the student is inaccurate and it does not have any precision. However, student B did not really hit the mark, but all the measurements were very close to each other. So this student is considered inaccurate, but it's precise. The third student, actually, all her measurements were close to each other and they were to the true value, which is 10 grams. Therefore, the third student was precise and had accuracy. When we are doing measurements, there is going to be a number that is going to be uncertain. That number is going to be reported last. Measurements are going to be done with different instruments. So the instrument is going to basically tell you how precise the number or uncertain digits that you have. When we have exact measurements, are actually not possible. There's always a level of uncertainty. And this is going to depend on the instrument that you're using. For example, if I have this nail here and you're using this ruler, some of you may say that this is a 2.85 centimeters. Some of you guys may say this is 2.86. What that means is that 2.8 is the certain value because we both agree on that. The last digit will be considered your uncertain value. Once again, I just want to remind you that this uncertainty is going to come from the instrument that you use. For example, in your lab, the the analytical balance will be the more precise. When it comes to volume, the volumetric, anything that is volumetric is going to be more precise. Most instruments are going to have a plus or minus number, and that tells you the level of uncertainty. For example, if it has a plus or minus 0.5, what that means is that the measurement that you have 0.5 centimeters of pretty much possibly mistake. So the instrument is going to go from either 9.5 to 10.5. So you want to make sure you pay attention, and this will be more clear when you get to the lab and you do some of those measurements. When we are doing averages, so for example, if you have certain, like 5 different people and you're taking their weight, when you are doing averages, averages have less or more significant digits than the measured number that makes them. So you can end up with more than what you originally started, or you can end up with less. So just want to keep that in mind for your averages. This is a question that you want to take time, read it, and try to figure out the answer. I hope you are correct. The answer is 1. Okay. The last topic for this chapter is going to be significant figures. Significant figures are actually going to contribute to the measurement, to the accuracy that you're doing. Most significant figures are going to be determined by you after I go over the rules. So before doing that, I just want to remind you that the last number is the estimated number and the other numbers are considered certain. Rules for significant figures. All non-zero digits are significant. So meaning anything 1 through 9 are significant. Interior zeros are also significant. So that's the numbers between the non-zeros. Leading zeros are not significant. So anything that comes before the actual integer, they're only there to serve as a placeholder. So for example, these zeros are not significant. Then we have trailing zeros, and this is where it gets a little bit tricky. These zeros after the decimal points actually are significant. The trailing zero before the decimal point are also significant because they're after the number between 1 and 9. Now, when you don't have a decimal place at the end, it's considered ambiguous. But if you want to turn it into not being ambiguous, you turn it into scientific notation. For example, this can be turned into 2 significant figures, 3 significant figures, and 4 significant figures, because now those zeros count as significant figures. Now, these rules, you're not gonna get good at just reading it. You must practice, 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 practice. Last thing I want to mention about this is that when you have an exact number, you give it as many significant figures as possible because it's a definition. So give them as many significant figures as needed. Here we have an example. This number has 4 significant figures. The second one is 5. This 0 is significant. This, uh, this last 0 is not significant because there is no decimal place. But once we put the decimal place there, now it becomes a significant figure. So now it becomes 5. This is ambiguous or 2. You can convert it to 3, 4, 5, however you want if you convert it to scientific notation. This is 3 because these ones are placeholder. Placeholder, significant. Placeholder, significant. So now try it on by yourself. When we are doing calculations, we shouldn't lose precision, or we should not gain precision. So this is very, very important when we are doing calculations. For example, if we are doing multiplication and division, that's the easiest rule. This has 3 significant figures. This has 5 significant figures. This has 2 significant figures. You're going to represent your answer with the least fewest number of significant figures. In this case is 2. So your answer will be 2. When we are doing division, the same rules applies. So we have 5 significant figures versus 3 significant figures. Your answer will be represented in 3 significant figures. The confusion comes when you are doing addition or subtraction. I highly recommend that you line up your decimal places. The rule is when you are doing addition and subtraction is that you're going to represent the answer as the least number of decimal places, least number, not significant figures. So notice that anything past this line is not significant. So therefore, you're only going to represent your answer in 3 significant figures. So make sure that you line them up. If you have scientific notation, convert it to standard notation. Rounding, it's something that you guys should be familiar with it already when you're rounding. First, do not round until you get to the end. Don't round anything until you get to the end. As a matter of fact, you might put a line just to remind you that you want to round, but do not round when you have a number. So because if you do round, it's going to affect your final answer. But if you do have to round at the end, if the digit to be removed is less than 5, the preceding digit stays the same. So for example, if you have this and you want to convert it to 2 significant figures, well, the number that follows, it's a 4, so you just drop it. However, if that number is greater than 5, you're going to increase it. So for example, this is a 6. It's going to become a 3.9. Things get a little bit more complicated when you have a multi-step calculations. Always remember PEMDAS, you want to start with a parenthesis first. Parenthesis, so go by this. What is that rule? If you were to do it, your answer from there, just from this, should be 0.48. But I told you not to round. So we're going to indicate a line saying that this is what is significant. Now you do multiplication. So this technically is 2 significant figures. This is 4 and this is 3. So your answer should be in 2. You'll have one of this on the exam. Here's some more practice for you guys to try, and we will do some together. But try to do it on your own, because this is where things start getting complicated. People start getting a little bit more confused. So practice them. I gave you the answers. And then when we meet, we'll do some more practice problems together. Your homework for this chapter has already been posted. At the end of these slides, you have practice problems along with the answers. I highly recommend them for you to do before your exam. It has the answers and we can always talk about it once you have completed them. Good luck. This completes the first chapter.